Year 12 Mechanics exam questions on forces and motion. We're going to have a look at a number of different types of question on forces and work through these. Make sure you have a copy of the questions as well. You may wish to work through the question and then look at the answer to check your working. If you're not sure about a question, once you've read it, you may wish to work through the question alongside the video. So let's start with question 1. So we're told that the resultant of this force and the force F gives an object a mass 6 kilograms and acceleration of 2/3 meters per second squared. So this is a question all about Newton's second law of motion. Remember, the resultant force is equal to mass multiplied by acceleration, and force and acceleration can be vector quantities in this context. They are vector quantities. And quite often we don't necessarily consider the whole vector, but in this case we are doing so. So we know that this force minus 4/8 plus the force F, it's in bold, there we go, it's a vector, equals the mass, which is 6 multiplied by the acceleration 2, 3. So we can rearrange this for F. F is equal to 12/18, subtract the vector negative 4/8, which gives us the force vector F as 16, 10. Part 2, we need to calculate the angle between F and the vector 0, 1. Now, what does the vector 0, 1 look like? If you had a set of axes like this, the vector 0, 1 looks like this. So what we're doing is looking for the angle between our force F and this vertical here. Now, 1626 would look perhaps like that, 16 along and 26 up. So if we complete the triangle, we want to work out this angle here. Now, our red vector there, 16 units along, 26 units up. We can use alternate angles to make it clear that this angle is also equal to angle theta. So theta is equal to tan minus 1 inverse tan of 16 over 26, which comes to a value of, this is equal to 31.607 or 31.6 degrees to 1 decimal place. Question 2. We have a pile of 4 uniform blocks in equilibrium on a horizontal table. The masses are as shown in the diagram. So we have to mark on the diagram the magnitude and direction of each of the forces acting on the 7 kilogram block. So the 7 kilogram block will have a weight which acts directly on it, which is 7g. And it will also be affected by the forces of the 4 kilogram block and the 5 kilogram block pushing down on it. If you imagine the 4 and the 5 kilogram block as one single object of mass 9 kilograms, this will result in a force of 9g pushing down on the 7 kilogram block. Now, there will also be a third force, which is the effect of the 10 kilogram block pushing upwards on the 7 kilogram block, which I've marked in green. Now, what's the magnitude of that force? Well, if you think about the forces acting on the 10 kilogram block, it's going to be affected by the force of the 4 kilogram block, the 5 kilogram block, and the 7 kilogram block, i.e. their 3 weights combined. So these 3 blocks will push down on the 10 kilogram block with a combined force of their total weight, which is 16g, if you add 4g, 5g and 7g together. Now, as a result, because the whole system is in equilibrium, the 10 kilogram block will also push upwards with an equal and opposite force to this. So that is the green force, which is 16g. So these are the 3 forces acting on the 7 kilogram block. Its own weight of 7g, the forces pushing down on it from the 4 kilogram and 5 kilogram blocks, and the force created by the 10 kilogram block pushing upwards on the 7 kilogram block. So a man of mass 75 kilograms is standing in a lift. Let's draw on the weight of the man acting downwards like that. He's holding a parcel of mass 5 kilograms, so that parcel has a weight of 5g. Now the man is standing on the floor of the lift, so the lift will be exerting a normal reaction force upwards on the man. The string here, which is holding up the parcel, has a tension of 55 newtons. We're told to find the upwards acceleration, so the lift must be moving upwards with some acceleration. Now, all of the contents of the lift will also experience the same acceleration, so what we will do is look at the forces acting on the parcel, and we will apply Newton's second law of motion, resultant forces, mass times acceleration, choosing up as our positive direction. So, tension acts upwards, the weight acts downwards, and this is equal to the mass, which is equal to 5, multiplied by the acceleration a. Rearranging this gives me an acceleration of 1.2 meters per second squared. Now, find the reaction of the man on the lift floor. So let's now look at the forces acting on the man, taking up as positive again. Now, before we do this, there is one last thing we need to add to our diagram. So the man is holding this string, and the string is attached to the parcel. Now, there is a tension force acting on the parcel upwards, 55 newtons. There must be an equal and opposite force of 55 newtons, essentially acting downwards like this in the man's hand, helping to produce that tension that keeps the parcel in the air on the end of the string. So, forces acting on the man using Newton's second law of motion. Now, upwards we have the normal reaction. Downwards we have the 75g, which is the weight, and we also have this 55 Newton force acting downwards as well. Now this is equal to the mass of the man, which is 75, multiplied by his acceleration, which is 1.2. This can then be rearranged to give us the normal reaction, which is equal to 880 newtons. Question 4, we've got a pulley question. We have two blocks of masses 3 kilograms and 5 kilograms connected by a light string, which passes over a smooth fixed pulley. Initially, the blocks are held at rest, but then they are released. Find the acceleration of the blocks when they start to move and the tension in the string. So we need to annotate our diagram with some forces. Here is the weight acting on the 3 kilogram block, the weight of the 3 kilogram block, the weight of the 5 kilogram block. There'll be a tension upwards like this, and the same here. Now, once the system is released from rest and it starts to move, the blocks start to move, the 5 kilogram block is heavier, so that will move downwards like this with some acceleration. The 3 kilogram block will move upwards like that. So we're going to look at using Newton's second law of motion again, force is equal to mass multiplied by acceleration. And we will start by looking at the forces on the 5 kilogram block, using down as positive because that's the direction of its motion. So the resultant force is the weight which acts downwards, which is positive. Subtract the tension, which is upwards, which equals the mass, 5 multiplied by the acceleration. Let's now look at the 3 kilogram block, and this time we will take up as the positive direction, which gives us T upwards, 3 kilogram block downwards equals the mass 3 multiplied by the acceleration. So we now have a pair of simultaneous equations. I'm going to add these together. So let's call this equation 1 and this equation 2. And we're going to add them together. So equation 1 plus equation 2. This gives us a nice opportunity to cancel out t and negative t, as you can see highlighted in red here. So equation 1 added equation 2 gives us 2g is equal to 8a. So the acceleration is equal to a quarter of g, which works out to be 2.45 meters per second squared. And then I'm going to substitute back into equation 2 to work out my value of the tension. So the tension equals 3G plus 3A, which comes out to a value of 36.75 newtons. Question 5. We have a block of mass 8 kilograms on a smooth horizontal table. So immediately I'm going to draw on the weight of the 8 kilogram block, so 8G acting downwards. I'll draw on the normal reaction acting upwards like that. The block is connected by a light string which passes over a smooth pulley to a block of mass 4 kilograms hanging freely. So let's move to our 4 kilogram object here, and let's draw its weight acting downwards like that, and then we'll draw in the tension in the string like that, which must be matched by another tension acting on the 8 kilogram block like this. So the system has an acceleration of 8 meters per second squared, which means this block here will accelerate downwards like that, and this block here will accelerate to the left like this. Part 1. Write down 2 equations of motion, one for each of the blocks. So when it refers to equations of motion, this means we are using Newton's second law of motion. So resultant force is equal to mass multiplied by acceleration. So for part 1, I'm going to start off by applying this law to the 8 kilogram block. I'm going to choose the direction of left, the direction of the tension or the direction of the movement, to be the positive direction. Now vertically, the forces acting on the 8 kilogram block are balanced. The normal reaction is equal to the weight of 8G. Nothing much interesting is happening vertically, but there is movement horizontally. There is an acceleration, and the resultant force is simply equal to T because there are no other horizontal forces acting. This equals the mass of the object 8 multiplied by the acceleration A, and we have one equation. Now the 4 kilogram block, I will choose down as the positive direction because that's its direction of motion. So I have 4G downwards, T upwards, so it's negative, equals the mass, which is 4 multiplied by the acceleration. Again, I don't know the value of the acceleration yet. Part 2 says find the value of the acceleration. So we've been here before. We're going to add equation 1 and equation 2 together, these simultaneous equations. So as we've been seeing in these examples, we have a negative t and a t, so they can cancel out easily. There are other ways you can solve these simultaneous equations. You can substitute one into the other, all manner of correct algebraic procedures, but adding to them together, if there is a plus t and a minus t, is a very simple way of doing this. This then gives me 4G is equal to 12A, so A very simply equals 1/3 of G in exact form, or if we work this out, this comes to a value of 3.26 recurring meters per second squared. Question 6 is all about 3 connected objects. We have a 6 kilogram block on a smooth horizontal table. So it has a weight of 6G, like that, and then that's balanced by a normal reaction of the table pushing up on the block. We're connected to 2 blocks of mass 2 kilograms and 9 kilograms. So let's draw in the weights, the 2 kilogram block 2G, the 9 kilogram block 9G. And we have tensions in the string. So we have a tension like that, which I'll call T1, and a tension like that, which I'll call T2. These are 2 different strings. Note the wording in the question, 2 light strings, which means that there are 2 different tensions, a different tension in each string. So we need to make sure that there's a tension which matches T1 here, which acts on the 6 kilogram block, and a tension here, T2, which matches the other tension in the second string. Right. Part 1 asks us to draw 3 separate diagrams showing all the forces acting each of the blocks. Now in an exam situation you would separately draw out the 3 force diagrams, but I'm not going to do that here. The 3 separate diagrams would just look like the 3 diagrams that I've drawn. This is the diagram for the 2 kilogram block, the diagram for the 6 kilogram block, and the diagram for the 9 kilogram block as well. So, part 2, calculate the acceleration of the system and the tension in each string. So we're going to apply F equals ma, Newton's second law of motion, on each block separately. Let's start with the 2 kilogram block, choosing the positive direction. Now, because the 9 kilogram block is the heaviest block, I think the system will accelerate downwards like that, pulling the 6 kilogram block horizontally to the right like that, and raising the 2 kilogram block upwards like that. Let's start with the 2 kilogram block. So we're going to choose up as the positive direction. So I've got T1 upwards, I've got 2g downwards, and that equals the mass multiplied by the acceleration. Here is my first equation. Now, let's move on to the 6 kilogram block. We're interested in the movement to the right as our positive direction. So that gives me T2 minus T1, which is going in the negative direction, it's left, equals mass of 6 multiplied by the acceleration a. Here is my second equation. Now my third equation of motion is going to result from analysing the 9 kilogram block and choosing down as positive. So we have 9g minus T2 equals 9 multiplied by the acceleration. All 3 blocks experience the same acceleration because everything is connected together and the strings are light and inextensible. Now, if we notice very carefully here, we have a positive T1 and a negative T1, so equations 1 and 2 added will cancel out the T1s. Equations 2 and 3 will cancel out the T2s, so what we're going to do is add equation 1, equation 2, and equation 3. So this leaves us with 9g take away 2g, which is 7g, and on the right hand side we have 17a. So a is equal to 7/17 of g, which simplifies to an answer of 4.0352 ... or 4.04 meters per second to 3 significant figures. But remember, we have now got to calculate the tension in each string, so we need to go back and calculate the values of T1 and T2. So think about how we store values in a memory. Because we've got the acceleration a, I recommend we put this in memory A. Substitute back into this equation perhaps, and then maybe this equation to calculate T1 and T2. So this then gives us T1 is equal to 27.67 ... or 27.7 newtons, and we get a value for T2 of 51.882 newtons or 51.9 newtons, both answers rounded to 3 significant figures. Question 7. We've got blocks of mass 4 kilograms and 6 kilograms on a smooth horizontal table. Here is the weight of the 4 kilogram block downwards, acting downwards, and the weight of the 6 kilogram block acting downwards. Now, each of these will experience a normal reaction force of the ground pushing upwards on them. They are different objects. They will have different reaction forces. It is important that we label them correctly like that. Now, they're connected by a light, inextensible string. So some key modelling words here. So we will have a tension like that and a tension like that. It's the same string and it's inextensible, so the same value of the tension throughout. So as shown, a horizontal force F acts on the 4 kilogram block and a horizontal force of 30 newtons acts on the 6 kilogram block, and we can see those forces marked on the diagram. Now, find the 2 possible values of F. So, we are told that the acceleration of the system is 2 meters per second. What we don't know is whether the system accelerates to the left or whether the system accelerates to the right, i.e., is F bigger than 30, so it can pull the whole system along to the left, or is 30 newtons bigger than F, in which case the system accelerates to the right. So that's where the 2 options come from. So what we're going to do for part 1 is, first of all, imagine that the system accelerates to the right like that, with an acceleration of 2 meters per second squared. So what I'm going to do is look at the forces acting separately on the two objects which are being modelled as particles. So 6 kilogram force first of all. Remember, we will be applying Newton's second law of motion, F equals ma, throughout this. I'm going to choose going to the right as positive because that's the direction of the acceleration, and that's going to be the same for both objects. So we have 30 newtons to the right, t to the left, which equals the mass, 6, multiplied by the acceleration of the system, which is 2. So from here, we can work out the value of t straight away, which comes to 18 newtons. If we then look at the 4 kilogram object, we have t going to the right, we have F going to the left, and this is equal to the mass of the object 4 multiplied by the acceleration 2. But we know that t is equal to 18, so 18 minus F is equal to 8, F is equal to 10 newtons, which indeed is smaller than 30 newtons, which makes sense as to why the system accelerates to the right. Now, because we treated the two objects separately when we applied F equals ma, we actually find out both values of F and the tension. So actually we're doing parts 1 and 2 together. If we'd treated the system as a whole, so as an object of mass 10 kilograms with a force of 30 newtons and in one direction and a force of F in the other direction, we would have just calculated the value of F, but we would have then had to separately split the system up and look at the two particles separately. Let's now look at the alternative scenario, which is that the acceleration is in this direction. So that's 2 meters per second squared to the left. We'll take going to the left as positive. So on the 6 kilogram force, first of all, what do we have? We have the tension in the positive direction. We have 30 newtons in the opposite direction equals the mass multiplied by the acceleration of 2, which gives me tension is equal to 42 newtons. Now, what about the 4 kilogram block? I've got F going to the left in the positive direction, T going to the right in the opposite direction, equals the mass 4 multiplied by the acceleration 2. We know that T is equal to 42, so this rearranges to give us F equals 50 newtons, and you can then see clearly F is bigger than the 30 newton force, which is why the system accelerates to the left. Question 8. We have a sledge of mass 40 kilograms. It's being pulled across a horizontal surface of deep snow by a light horizontal rope, and there is constant resistance to its motion. There's a little diagram of it here. So first of all, it's got a mass of 40 kilograms, which means it's got a weight acting downwards of 40 g. There must be a normal reaction of the ground pushing up on the sledge, which we'll call R, like that, vertically upwards. Now, there is a light horizontal rope, which has a force of 120 newtons marked on the diagram, and there is a constant resistance to the motion. Now, think about resistance and friction. They oppose the direction of the motion or the intended direction of the motion. The 120 newtons is attempting to move the block in this direction here, to the right, which means the friction must be opposing that movement, and the friction must be in this direction like that, the resistance, like so. Now the sledge is initially at rest. After 10 seconds, its speed is 5 meters per second. Now, what can we calculate with that information? We can calculate the acceleration using the equations of constant acceleration, the Suvat equations. Why can I use a Suvat equation? Well, forces acting are constant, which means resultant force will be constant, which means by Newton's second law of motion, F equals ma. If sigma F, the resultant force, is constant because the mass is constant, acceleration will also be constant as well. So having justified my constant acceleration, let's fill in the Suvat information and see what we know. So we don't know the distance travelled. Initially at rest, so u equals 0. V is 5 meters per second. Acceleration, we don't know, and the time is equal to 10 seconds. So what can I calculate from here? Well, I can get rid of s, and I can look at calculating the acceleration using v equals u plus at. 5 equals 0. plus 10a, and that gives me an acceleration of 0.5 meters per second squared. Now, show that the resistance to motion in part 1 is 100 newtons. So let's take going to the right as positive. Let's apply Newton's second law of motion, which we helpfully wrote up here earlier on. Right is positive, so we've got 120 newtons to the right. Take away the resistance, which acts to the left, which is equal to the mass, which is 40, multiplied by the acceleration, which we just worked out as 0.5. It's then quite a simple process to rearrange this and work out that the resistance is equal to 120 subtract 20, which is the required 100 newtons. Now, when the speed of the sledge is 5 meters per second, the rope breaks. Now, what is the impact of that? Well, it means that this 120 newton force, that is no longer there. So if you were to look at a sketch diagram of the situation, you would have the sledge, there's its weight downwards, there's the normal reaction upwards, and we just simply have the resistance force like that. So what do we know? The resistance force is still equal to 100 newtons, and we need to find the speed of the sledge at these two times. So we need to know the new acceleration. Why will the acceleration change? Well, previously the 120 newton force was pulling the object along, and that gave it its acceleration, essentially. That's no longer there. So we have to recalculate what the acceleration will be without the presence of this force. So I'm going to take going to the right as positive. I have no forces acting in the direction that I've labelled as positive, but I have 100 newtons in the negative direction. So my F equals ma gives me minus 100 equals the mass 40 multiplied by the new acceleration, which gives me an acceleration of minus 2.5 meters per second squared. What does that mean? We've got a deceleration. So of course, the resistance force is causing the sledge to slow down because there is no 120 newton force pulling it along like that. So we now need to use this to work out the speed of the sledge at these two times. So this is all going to be about suvat again. So S, we don't know. U is the initial speed when this process starts and the rope breaks. So U is 5. V is what we're actually trying to find, so that's quite important. A is minus 2.5, and then T is the time, which varies in part A and part B. So ruling out S, we can then make use of V equals U plus AT. So let me look at part A first of all, where T equals 1.6. V then equals 5 minus 2.5 multiplied by 1.6, which comes to a speed of 1 meter per second. Now part B, T equals 6. This is going to give us an interesting result in a minute. V is equal to, then, 5 minus 2.5 multiplied by 6, which gives me a velocity of negative 10. Now, stop and think about this for a minute. It is not possible for the sledge to have turned around and to have started to move in the other direction. That's not going to happen. So what's happened is we've got kind of a false result here, and actually the sledge has stopped. The sledge at some point must have hit a velocity of 0 or speed of 0. And in fact, there isn't a huge amount of space, but I'll work it out up here. Let's imagine V equals 0. So let's take our equation V equals U plus AT, and I'll say 0 is equal to U, which is 5. Now the acceleration is minus 2.5 multiplied by t. Now if I rearrange this, this gives me t equals 2 seconds. So at 2 seconds, the sledge actually stopped moving. So at 6 seconds, it's stationary. So the speed of the sledge is actually equal to 0. We've just got a sort of a false result from the calculation, but there is no way that the sledge is travelling at a speed of 10 metres per second in the opposite direction. It's not changed direction. Question 9. So, figure 4, we have boxes P and Q descending vertically and supported by a parachute. Box P has a mass of 75 kilograms and box Q has a mass of 25 kilograms and hangs from box P by means of a light vertical wire. Air resistance on the boxes should be neglected. So at one point, the boxes are slowing in their descent, with the parachute exerting an upward vertical force of 1,030 newtons on box P. The acceleration of the boxes is a meters per second upwards, and the tension in the wire is T newtons. So part 1 wants us to draw a labelled diagram showing all the forces acting on P, and then another separate diagram showing the forces acting on Q. So if we start with box P, so we know that there will be a vertical upwards force like that due to the parachute, which is 1,030 newtons, like so. Now, P has a weight of 75 G, so we can include that as well. And then we also know there must be a tension in the wire like that. So we have these three forces acting on box P. Now, box Q, P and Q are connected by the same wire, so there must be a tension force upwards like that in the wire. And then we, of course, have the weight of Q, which is 25 G, as demonstrated. Part 2. Write down separate equations of motion for box P and for box Q. So for box P, first of all, we will take up as the positive direction in both cases. So we have 1,030 minus 75G minus T equals 75A. And then for box Q, also taking upwards as positive, we have T take away 25G equals 25A. Part 3 asks us to calculate the tension in the wire. So note that if we can, of course, see our negative T and our positive T here and add these together. So that's 1,030 minus 100G equals 100A. And from there we can work out the acceleration, which is 0.5 meters per second squared. Substitute that into either equation to work out T, which comes to 257.5 newtons. So question 10, we have a cylindrical tub of mass 250 kilograms on a horizontal floor. Resistance to its motion, other than that due to friction, is negligible. So we have a weight of 250 G downwards, normal reaction upwards like that. It's being pulled with a force of 150 newtons like that, and there must be a resistance force, which I'll call curly F, friction, like that. Now, part 1, calculate the acceleration of the tub if friction is ignored. So that means that we're excluding that green force of friction, and actually the only horizontal force acting is this 150 Newton force. Let's take going to the right as positive. This will be the direction of our acceleration, and let us make use of Newton's second law of motion. Of course, resultant force equals mass multiplied by acceleration. So our resultant force is 150 to the right. That's the only force acting horizontally, which equals the mass 250 multiplied by the acceleration. So this gives me an acceleration of 0.6 meters per second squared. Now, things change. There is friction and the tub does not move. Write down the magnitude and direction of the frictional force opposing the pull. Well, if the system is in equilibrium, then that means that F, the friction force, must equal 150 newtons, which must act towards the left. Now, what's a good way of expressing that? Well, that's the negative I direction. So it's in the opposite direction to the 150 Newton force. So, question 11. Figure 5 shows two boxes. A of mass 12 kilograms, so here is A's weight, like that. B of mass 6 kilograms, there is B's weight, like that. And there will be normal reaction forces of the ground on each box, reaction force on A and reaction force on B. The boxes are connected by a light rigid rod, which is parallel to the line of motion. So there must be a tension pulling A like that, and a tension equal and opposite pulling B like that. The only forces acting on the boxes in the line of motion are those due to the rod and a constant force of F newtons on each box. And we can see F there, and we can see F there. I've highlighted F in yellow on both boxes. Now the boxes have an initial speed of 1.5 meters per second, and they come to rest after sliding a distance of 0.35 meters. This is instantly giving us some SUVAT information with which we can work. So our SUVAT information tells us constant acceleration equations. S is 0.375 meters. U is equal to 1.5, the initial speed. V equals 0 because they come to rest. A is what we're looking for, and we don't know anything about the time, and actually that's not useful to us. So the equation we want is V squared equals U squared plus 2AS. 0 is equal to 1.5 squared plus 2 multiplied by A, which we're trying to work out, multiplied by 0.375. Rearrange to give you a value of A, which comes to -3 meters per second squared. It's a deceleration, which makes sense because the box is coming to rest. So part 1, calculate the deceleration of the boxes. We've got that, -3 meters per second squared. Now to calculate the value of F. Now to do this, we're going to need to look at the forces acting. Now, one way we can do that is to combine the two of them as one single box, which will cancel out the two green T forces, but we then have to later on, you can see in part 2, find the forces in the rod. So what I'm going to do is look at the particles separately. I'm going to start with object A. I'm going to say going to the right is the positive direction. So I have F equals ma, my Newton's second law of motion. Let's write it down to always remind ourselves there. So I have T to the right minus F to the left equals the mass of 12 multiplied by the acceleration of -3. So there is one equation. Now, let's look at the forces acting on particle B this time. So what do we have? We have, again, we're going to choose going to the right as positive. This time we have -T, because that's to the left, -F, also to the left, and that equals the mass of B, which is 6, multiplied by the acceleration of -3. So we have a second equation, equation 1, equation 2. Now, let's think about what we need to do. We need to calculate the value of F. So I'm going to think about the fact that I've got a positive T and a negative T. So if I add these two equations together, positive T and negative T will cancel out. I end up with -2F on the left-hand side of the calculation. And on the right-hand side of the calculation, I get -54. This then simplifies to give me F equals 27 newtons. Now, part 2 says we need to calculate the magnitude of the force in the rod and state with a reason whether it is a tension or a thrust or compression. So, let's work out the size of the force T, looking at objects A and B separately to see what happens. So T minus F equals -36. We know that F is 27, so T minus 27 equals -36, which gives me T is equal to -9 newtons, which is interesting. Now, in equation 2, if I work this out, this tells me that T is equal to 18 minus F, if I rearrange, which gives me 18 minus 27, which is also -9 newtons. So let's think about the system again and how it looked. So A and object B like that, they were connected like that. Now, we said going to the right was the positive direction, and the force acting on A, we had drawn it going to the right, but it worked out to be -9, which means that this force acting on A looks like that. So it should have been like that. Now, for B, we also got a value of -9. But if you look at the fact that we had originally drawn the force of T acting on B going to the left, that means that result should have worked out to be a positive value of 9. The fact that we've got another negative value means that actually it should look like that. Now, this means that the forces in the rod, so remember these T forces that we've just drawn on the diagram are forces acting on A and B, the forces in the rod will oppose these, so there'll be a force like that in the rod opposing this force here acting on A, and there'll be a force like this in the rod opposing this force T like that. And can you see these forces are pushing in? So the rod is in compression. The forces in the rod are pushing it inwards, not pulling it outwards. So it's in compression or thrust. Question 12. So we have a locomotive L pulling two trucks A and B. I'm going to actually do another sketch of this diagram here because the shapes given make it a little bit difficult to draw on all of the forces acting. So we'll model everything as a particle, all three objects as a particle. So the locomotive has a mass of 90 tonnes, so 90,000 kilograms. 90,000 G is its weight. Trucks A and B have masses of 30,000 kilograms, so their weights are 30,000 G. There will be normal reaction forces acting vertically upwards like this, which I will just draw on as RL, RA and RB. And let's draw on the couplings between the locomotive of an A and between trucks A and B. Now there are resistance forces, you can see. The locomotive is subject to a resistance force of 2,000 newtons, and A and B are subject to resistances of 500 newtons each. And we have some tensions in the coupling, or some forces, let's say, in the couplings. Let's call this T1 and T1 there, between A and L. And because it's a different coupling, let's call this T2 and T2 here, between A and B. So we have all the forces drawn on acting on L, A and B in our model. Now, there's one last piece of information. The locomotive is exerting a driving force of 12,000 newtons. So I'm going to put that on in yellow, 12,000. Some very large numbers here in this question. Find the acceleration of the train. So I'm going to draw on my acceleration like that. I'm going to say going to the right is positive. Let's look at the forces acting on each object individually, each particle. Let's start with L. So I've got 12,000 going to the right, take away T1, take away 2,000, those two going to the left, equals 90,000 multiplied by the acceleration. Forces acting on A, again, the right is positive, so this time I've got T1, take away T2, take away 500, equals 30,000 A. And then forces acting on B, I've got T2, take away 500, equals 30,000 A. Now, let's add these three equations together as we've done in the past, because we have that very convenient situation where positive and negatives of the same value will cancel, and this leaves me with 9,000 equal to 150,000 A. So we can work out the value of A, which is 0.06 meters per second squared. So this then allows us to calculate the tension in the coupling between trucks A and B, which is T2. So if I substitute back into the third equation, T2 equals 2,300 newtons. Now, when the train is travelling at 10 meters per second, A fault occurs with truck A and the resistance to its motion changes from 500 to 5,000 newtons. The driver then reduces the driving force to 0 and allows the train to slow down under the resistance forces and come to a stop. Find the distance the train travels while slowing down and coming to a stop. So we need a new diagram because the system has changed. So I'm going to draw a new diagram here because things have changed. So here are my three objects, the locomotive, A and B. Now the driving force is now 0, so that has disappeared. Truck A now has a resistance force of 5,000 newtons. Truck B has, we assume, an unchanged resistance force of 500 newtons. Now, I'm not going to draw on the vertical forces here because I'm less interested in those. I'm looking at the horizontal forces acting. So let's join up the objects and let's mark on T1 here in the coupling here and T2 over here, and these are the forces acting. Now, we can now recalculate using F equals ma, the new acceleration. Let's take going to the right as the positive direction, and let's look at the individual forces acting on each of the particles in turn. So force L first of all, well, we are missing actually currently its resistance force, which was 2,000 newtons. We should put that in. So for force L, we have negative 2,000 minus T1 equals its mass of 90,000 multiplied by the new acceleration. Object A, we have T1 going to the right, take away T2, take away 5,000 equals the mass, which was 30,000 multiplied by the acceleration. And then object B, we simply have T2 going to the right, take away 500 equals the mass, 30,000 multiplied by the acceleration. Now again, we can add these three equations together. Let's see what will cancel. T1 and T1, negative and positive there. Negative T2 and T2, they will cancel as well. So that leaves me with, on the left-hand side, negative 7,500, and on the right-hand side, I have again 150,000 A. So acceleration is equal to negative 0.05 meters per second squared. So we need to find the distance the train travels while slowing down and slowly coming to a stop. So we're going to use SUVAT here. Let's see the information that we need. S is what we're looking for. Be careful, that's an S, not a 5. U is the speed we are initially travelling at, which we're told in the question is 10. V equals 0 because we're looking at the train coming to a stop. Acceleration is equal to negative 0.05 and time we do not know. So using V squared equals U squared plus 2AS, 0 equals 10 squared minus 2 times 0.05 multiplied by the distance travelled gives the distance travelled as 1,000 metres. So the last part of the question asks us to find the force in the coupling between trucks A and B while the train is slowing down. So that's force T2, which we can use this equation to calculate. So T2 equals 500 plus 30,000 multiplied by the acceleration of negative 0.05, and this gives T2 as negative 1,000 newtons. Now, remember the connection between particle B, or object B, and object A. Now, we defined going to the right as positive, and the force, the tension force that we drew on object B was in that direction, but T2 has worked out to be negative 1,000 newtons, which means that the force T2 acting on B must be like that, in that direction, and there is an equal and opposite force acting on A like that. which must actually be in this direction. Now, if we then focus on the actual coupling here and think about the forces acting in this, there must be an equal and opposite force like that and an equal and opposite force like that. So if we look at the forces in the coupling, they are pushing inwards like that, which means the coupling is in compression. It's being squashed. It's not being stretched. It's not in tension. So it's in compression, or as we sometimes call this, thrust. Either of these two words can be used. Question 13. Robin is driving a car of mass 800 kilograms along a straight horizontal road at a speed of 40 metres per second. Robin applies the brakes and the car decelerates uniformly, coming to rest after travelling a distance of 125 metres. So part 1, show that the resistance force on the car when the brakes are applied is 5,120 newtons. First thing we're going to do is apply suvat to see what we can calculate, whether we can calculate the acceleration. S is 125 metres, U is 40 metres per second, V is 0, A we're trying to calculate, and T we do not know the value of. So applying suvat, we can use V squared equals U squared plus 2AS. So let's substitute into this, and this then leaves us with a value of the acceleration as negative 6.4 metres per second squared. Now, if we then think about the forces acting on the car, so we know that, well, we have a normal reaction force acting upwards, we have the weight of the car acting downwards like that, and we know that there is a braking force which essentially generates this sort of resistance force, which we will call F. So I will take this direction as positive, and then F equals ma. So we know that negative F is the mass, 800, multiplied by the acceleration, negative 6.4, which gives us our force value as 5,120 newtons. Part 2, really simple. Find the time the car takes to come to rest. Well, we had all the suvat information set up earlier. We can use V equals U plus AT, 0 equals 40 minus 6.4t. Now we know the acceleration, so the time works out to be 6.25 seconds. Now, the rest of this question is really more based on kinematics than it is on forces and motion, but let's take a look at it. So, we assume that there is a constant resistance force of 5,120 newtons on the car. The car returns to its speed of 40 metres per second, and the road remains straight and horizontal. Robin sees a red light 155 metres ahead, takes a short time to react, and then applies the brakes. The car comes to rest before it reaches the red light. Show that Robin's reaction time is less than 0.5 seconds. Part 3. So we know that the red light is 155 metres ahead, and we know that the stopping distance from earlier on is 125 metres. So we need to calculate the reaction distance, which is equal to the total distance away to the red light, subtract the stopping distance required for a car travelling at this speed, which is 125 metres. So the reaction distance, as we'll call it, is 30 metres. Now, we can use speed equals distance over time because the car is travelling a very short distance at 40 metres per second. So speed equals distance over time, which of course means time equals distance divided by speed, which is 30 divided by 40, which is 0.75 seconds. So the reaction time will be less than 0.75 seconds because the reaction distance is going to be just less than 30 metres. So the stopping distance is the total distance travelled while a driver reacts and then applies the brakes to bring the car to rest. For the rest of this question, assume that Robin is still driving the car described above and has a reaction time of 0.675 seconds. calculate the stopping distance when Robin is driving 20 metres per second at 20 metres per second on a horizontal road. So the stopping distance is going to be made up of two components. One of these components is the distance travelled before the brakes are applied, so almost like a reaction distance, plus the distance travelled during the braking process. Now, the distance travelled before braking, speed equals distance over time, or distance equals speed times time. Well, we know that the speed is 20 metres per second. Multiply that by the time, the reaction time. Remember, we said this is the reaction distance first of all, so that's 0.675 seconds. And then we need to add the distance travelled during the braking process. Now, that is going to require the use of a Suvat equation. So we can make use of v squared equals u squared plus 2as. So that's 0 because it's stationary at the end. 20 squared plus 2 multiplied by the acceleration negative 6.4, which we worked out earlier on, multiplied by s, which is what we're trying to calculate. So this then gives us an s value, which will be equal to 20 squared divided by 2 multiplied by 6.4. We can then calculate the overall stopping distance. So this gives me 13.5 plus 31.25, which comes to 44.75 metres. Now, just to clarify, I was able to use an acceleration of negative 6.4 because earlier on we're told in the question that we assume that when Robin applies the brakes, there is a constant resistance force of 5,120 newtons, and using F equals ma, that means the acceleration will consistently have a value of negative 6.4.